All right, guys, I think I'll go ahead and get started. We could have some latecomers, which is also fine, either in person or in Zoom. But I'm glad you guys are here. I am going to be focusing on practicing sample exam problems. This is out of a document in the Midterm 1 resources folder. It's called Midterm 1 Review Session. And so there are 10 problems in this review session packet. It's somewhat intended to be comprehensive over all of the material, but I can't promise it's perfect with everything being perfectly covered all the time. But I did the best I could with it. Obviously, you should do more practice than just these problems. So you have 2 sample exams. I definitely hope that by the end of today, everybody would have at least tried one of the 2, if not both, but at least one of them to get an idea. And then obviously we have time tomorrow all the way up until 4 o'clock as well. But I'm not going to go over those problems because, of course, I have the solutions to all of that in Canvas already. Same thing with the group works. I highly recommend reviewing those, but I won't go over those now unless there's specific questions about them. I think what I'd rather do here is tackle these fresh problems, even though I do have them solved in the resources folder. You can find the solutions all worked out. I'm going to just take these kind of at face value as practice problems to start from. And instead of just having you read the solutions, we can talk through it a little bit, which I think is actually a better way to kind of learn it anyway, if we talk about it. And by the way, this is super casual. This is not like a lecture where I have to cover certain material or anything like that. I have no agenda for this. It doesn't matter. So please interrupt me with questions, clarifications. It can be something about the actual math, but it could also be something about, if this was on an exam, would you expect X, Y, and Z? And you can always ask me. I should say, obviously, I'm going to be at the exam. So if you are not sure you understand the question exactly, you should feel free to come up and ask me about it. That's not cheating. If I don't think I can answer it, I'll just say I don't think I can answer that. But you have nothing to lose if you're a little unclear on something, because I don't want people to get the questions wrong just because they didn't understand the question for sure. So you should feel free to come up and ask me about anything in terms of questions as we go along, okay? That's during the exam. Also, try to manage your time carefully. People have been asking me if I'm going to let them take home anything, because on the sample test, you might have noticed I allowed students to take something home and then submit it later into Canvas. I have not written the test yet, so I don't know if I will be doing that. I always wait till after my review sessions to do that, but it's definitely possible. And if that's the case, you should strategize what you're taking home and use the in-class time to your maximum benefit as best as you can. Don't spend 20 minutes on something that you're going to take home anyway. Just let it go and focus on the other things, okay? Also on explanations, if you write out an explanation, let's say this is equal to 30 choose 16 because we have 16 bars and 14 stars. You can explain that. It's a good thing to do. Have a little note there on the side. If the answer is there, but it's wrong and there's nothing to justify with it, then I can't give you partial credit really for anything. So write down your reasoning. And if I realize, oh, well, they had the number of bars right, they were just wrong on the stars, and they knew it was a stars and bars problem. So I'm not going to take off as much credit for that as I would if it was just completely wrong. So I highly recommend that you write little. Doesn't have to take a long time, and it doesn't have to be perfect English. Just a little note about what the expressions you're writing down would represent. However, if you have essentially the same expressions, let's say you're doing inclusion exclusion and you end up subtracting a bunch of violations and then adding some two-way violations and all of these kinds of things back in, if you actually explain every single one of them, you've seen some examples where there's been like 10 or more of those, right? And it gets redundant. That's really not the best use of your time. I would probably explain one or two of them and then just let the rest of them go, or just say similar. The rest of them are all similar, and I'll get the idea that you know what you're doing. Okay, so just in terms of showing work, it's good to show your work and explain what you're doing. In fact, I almost expect that in this kind of a class. If you want to get credit for an answer, it's got to be explained. But if you are repeating the same explanation again and again, and you catch yourself doing that, watching the clock go by, that's probably the time to sort of just put a similarly note on your paper and kind of go on. You can always come back to it later if you have more time, but I would definitely recommend that you justify your answers, but not repeating the same justifications again and again. So I was just going to say something about that. So some of this is just about test taking strategy, and you know why I'm doing it is because I have students who really know the material well, who sometimes don't score that good on the test because their explanations are missing. And I also have kind of the other way around. People are kind of very loosey-goosey. They don't have any of the answers really correct, but they have lots of good explanations there that I can give lots of credit for. And so even though you might on the surface think, oh, they didn't get anything right, well, actually, they have a lot of the right ideas there. But the key thing is to get it written down, the justifications written down. So I'm just thinking in terms of test-taking strategy to try to help yourself out by help me to help you with partial credit by writing down your thoughts about the answers that you're putting down. My tests do tend to be long. I tend to be comprehensive. I get excited about math. So my problem is I get to a question, oh, this is a great question. I got to ask them about that. And oh, this is a great question. I got to ask them about that. And I tend to do that a lot. So it's sort of on me. If the test is too long, that's on me and I have to fix it later. But having said that, just knowing going in that there will be a lot to do. There probably won't be a lot of topics that we covered that you won't see. I will probably find a way to make sure that everything is in there. The pigeonhole principle, all types of permutations and combinations, some where you use just the multiplication principle, some where you have to use stars and bars, some where you maybe have to subtract some violations. It's any of these tricks that you've seen, very good chance I will find ways to get questions about almost everything I can think of in there. There's surely going to be a problem on combinatorial argument, right? You will certainly have to do a problem like that. There will certainly be an application or two of the binomial theorem and or the multinomial theorem. I'm just going over the big picture topics here for a moment. And I know, and if you're taking notes on this, by the way, don't forget that's totally good to do that, but keep in mind, I am recording this and I will send it out. So if you're frantically trying to keep up with me, no need to do that. Oh, and don't forget about the pigeonhole principle. So we've seen some examples of that. Even on the quiz, there was a little problem about that too. So those kinds of things are quite likely. And then more recently, of course, we've talked about forbidden positions and as a special case of that, derangements. And I would be surprised if there isn't something along those lines for you to do as well for the exam. So, okay, I'll try to model this a little bit as we do these practice problems. I'll model kind of what to write down, what I would expect. And you guys can ask me if you think it's too much or if you think it's too little of a write-up, and I'll try my best to give you what I think about that. So there are 5 problems from the 10 that are in this review packet, 10 choose 5, that I did not cover in the first review session, which was presented to you as a video. Did you see that yet? Okay. So I'm not going to repeat those problems, at least not right away. Is there any more eraser in this problem there? Thanks. I'm not going to repeat those same questions again. So the ones on the review session that I did not do number 2 on the first session. I did not do number 4. I did not do 5E either. I'll come back to that one. Number 6 I did not do. And then number 9 and number 10. So these are I guess it's actually 5.5 parts here. that we didn't do. So I'm gonna do these not necessarily in order. I'm gonna kind of just jump around a little bit. I think I'm gonna start with number 9 as a good place to start with these examples. So this is a problem about a bagel shop. By the way, I really liked that, Lindsay, that it wasn't a bagel you got me, but that thing.
Oh, the little bunny.
It was so good. So
Yeah,
good. Yeah, thank you for doing that. Okay, so number 9, a bagel shop has flavors. And let me know if you can't see anything out there in Zoom land. I'm gonna try to write this big enough to be able to see this. So there's onion, there's poppy seed, there's egg, there's salty bagels, there's pumpernickel, there's sesame, there's raisin, and then there's plain. We have all of these kinds of bagels, and then the question is, how many ways are there to select 6 bagels? So, and there's nothing else to the question but that's the only thing that's put there. So I usually like to try with these questions to ask 2 basic questions. One question that's a basic one, we've done these a lot, but does the order matter? Does the order matter? And then another question is repetition allowed? So I'm kind of reviewing, this is from the main chapter on combinations and permutations. 2 very, very important questions. Now, these questions do not always have an absolute clear-cut answer. Like, for example, with the Mississippi problem, in that question, some repetition is allowed, but it's not complete repetition. Like you can repeat certain letters, but maybe not others that don't have repetition. The order matters. Well, if it's the same letter, switching the order of the same letter in the string of Mississippi does not matter, but switching distinct letters would matter. So I'm not trying to say that this is going to have a perfect blueprint answers that will work on every problem, but it's a really good place to start. And if you can answer these in sort of a black and white way that's like clear cut, it will very much dictate and help you to decide what to do here. Because, for example, if I know that order matters and repetition is allowed, I can think about what kind of problem I've seen that's like that. And you'll probably think about things like license plates. Okay, the order matters, but you can repeat the same character again and again. Or if I say the order doesn't matter and repetition is not allowed, so that would be like poker cards. So you have a hand of cards, there's no repeats there. So then you can think about it in terms of, well, what kind of expressions would I use if this was about poker cards? So I do, hello, come on in.
Hi.
So I do like to, we're just getting started. I did a 10-minute preamble about strategy for the exam though. So it's being recorded and you can pick up the first part of it later if you need to. Yeah, so on any of these counting problems, arrangements and so on, I always like to start with these questions. Does the order matter and is repetition allowed? So on this problem, would you guys say the bagel shop problem, we have all these different kinds of bagels. How many ways are there to select 6 bagels? Would the order of that selection matter? No, definitely not. And is repetition allowed?
Oh, yes.
I could pick up several onion bagels and several poppy seed bagels and so on. So I would say that this is a yes, right? Repetition is allowed, but the order doesn't matter on this problem. Now, keep in mind, I could change the question a little bit. I could say, how many ways are there to select 6 bagels if you cannot take more than one of any kind. Well, that would be changing repetition allowed to a no, just like that. And it would be completely changing the answer. This is the other thing, guys, is that the way the answer looks for the cases of yeses and nos here is extremely different, right? I mean, you go from a stars and bars kind of an answer to something that looks like a power of a number kind of an answer. And so it can look really different depending on what the answer is. In this case, if the order doesn't matter and repetition is allowed, what kind of problem is that? That's stars and bars, exactly. So this is stars and bars. So now I'll go ahead and start doing the solution. Stars and bars. And the bars are used to separate out what?
Separate the flavors of the bar.
The different flavors of the bagels, right? So you have to figure out how many you have here. 1, 2, 3, 4, 5, 6, 7. There's 8 different kinds of bagels. So how many bars would you need to split out 8 different kinds of bagels? 7, right? So there will be 7 bars. And I might just say to separate. What I'm doing right now is writing what I would write if I was a student taking the test. So you're like, you don't just write 7 with no justification, because even if it's correct, I'm not gonna be real happy, but also if it's wrong, let's say you accidentally counted this wrong. Anybody could do, I could do that, right? If you counted it wrong and all you had was a number here and there was nothing to explaining it, then I can't really give you much partial credit. I want to give you partial credit. So let's add a note here. What are we talking about? To separate the flavors, and say the 8 flavors of bagels. So we use 7 bars, and then how many stars will we have? 6, that's how many bagels we're choosing. So choosing the bagels here. Okay, so it doesn't have to be anything that takes a lot of your time, but just quick little notes to yourself about what everything represents is great, just in case you have a mistake, and just so I can give you partial credit in that case. So what would be the answer to this problem? How many ways are there to select 6 bagels? If I have 6 stars and 7 bars, it's going to be?
Choose 6.
13, choose 6, which by the way is also 13, choose 7. I would take either one of those as an answer. You add up the stars and bars. It's an arrangement of 6 stars and 7 bars in a 13 positions, right? And you're just choosing the positions for either the stars or for the bars. I will tell you that I generally prefer to put the bars on the bottom. I prefer that. The reason being that if I now have some violations and I want to give you some changes to the number of bagels here of certain conditions, the number of bars usually stays the same. So I just like having that number on the bottom just always staying the same rather than having to keep fixing it every single time. So yeah, that's all there is to that. That's pretty straightforward. So 6 bagels. By the way, this is typical of me when I'm writing a question like this, is to have several parts. The first part is just sort of a warm up. There's no constraints here at all, not making any extra conditions. So let's go on to part B. These are the problems I'm going to be going over from the review packet. I'm currently starting with number 9. So part B is, how many ways are there to select a dozen bagels? Now, if you didn't know what a dozen was, most people probably know that's 12, but if you didn't know that, just come up to the front of the room and ask me, right? There's nothing wrong with doing that. A dozen bagels with at least one of each kind. So how many ways are there to select 12 bagels? This is 12. And I want to have at least one of each kind. Any thoughts about how we have to think about this one?
I wanted to say stars and bars where you just pick one of each first and then you.
It's like I talked about the grocery store example where you go in and you grab your apples, take them back to the car and then start over. And you haven't really made any choices yet. Yeah, so you could definitely do that. So for the solution, we first, notice I'm gonna write down a little explanation. So first, grab one of each kind. And there's no choices being made right now. We're just going ahead and forcing ourselves to grab one of each kind. And this leaves us, so leaving 12 minus 8, because there's 8 different kinds over here, 8 kinds of bagels. So leaving us with 4 more bagels to choose. Okay, so this doesn't have to take you very long. This takes 30 seconds, just write that down. And now you are looking for 4 bagels. You haven't made any choices yet. You just want 4 bagels. You still have all of these available. And so what would be the answer here? Maybe I'll just, so this is going to be the stars, right? And we still have 7 bars. So the answer would be 11 choose 7. So instead of 13 choose 7, it would be 11 choose 7. And you could just say on something like this, similar to part A. So here, you're not doing anything different than what you did in part A. So save yourself the time of re-explaining it the way I wrote these explanations. You wouldn't need to keep rewriting that again. So that was one of the things I was telling people in the little preview of the review was, if you have, something like this as an answer, because there's been some of these, right? You don't need to like go into each single one and each one of them have like all of this written down. You could maybe explain this one and maybe this one or something, and then just say the rest are similar, because otherwise you'll spend too much time like repeating the same justification again and again. Okay, great. So are we okay so far? Everybody doing okay? Great, let's do part C. And this one is a little bit longer. A dozen bagels. So we're gonna get 12 bagels again, a dozen bagels with, and then I have several conditions, at least 3 egg bagels. And then between 2 and 5 plain bagels. I'll just abbreviate that this way. So the plain bagels would be between 2 and 5. And then we want to have at most 2 raisin bagels. And then we want to have at most 2 sesame bagels. So this one's a little bit more. Let me get the camera over by the questions so people can read it if they're watching along the way here. Okay, so let's take a look at this one. All right. For this one, I might actually recommend that we set up some variables, one for each of the kinds of bagels over here. So if we come back over to the original setup of the problem, what I might do is, I might just let the number of onion bagels be x1, and then the poppy seed bagels could be x2, the egg bagels would be x3, and so on. You've noticed I've managed to get away without doing this on the first couple of parts, but this time it might be just easier to rephrase this problem using 8 different variables, x1 through x8. And what I'm going to do is try to create an equation. So I know that my 8 variables need to add up, ... My 8 variables need to add up to 12. And I can rephrase these conditions that are given in terms of the variables now. So the egg bagel was x3, so x3 needs to be at least 3. I'll just add that over here on the side. The plain bagel, that was the last variable, has to be between 2 and 5, so that's x8. x8 has to be between 2 and 5. The raisin bagel was x7, and that one has to be less than or equal to 2. And then the sesame bagel has to be also less than or equal to 2, and that was x6. So we can make our conditions kind of looking like this, what we have up here so far. Okay, so far so good, everyone? Okay, great. What I like to do with these conditions is I actually like to do a change of variables so that the lower number is always 0. So the minimum amount would be 0, so I don't have to take anything out right away. We could just take 3 stars out of the 12 immediately if we wanted to. And the same thing here, take 2 stars out of the x8. But personally, just to formalize it a little bit nicer, what I like to do is change variables and rephrase the entire problem. So change variables, and the changes of variables are based on the conditions that are giving us a lower bound on the variable. So for example, guys, y3 would be x3 minus 3. So that is now bounded on the bottom by 0. And y8 would be x8 minus 2. Again, that's based on this condition here, right? So sometimes people get these, the way this one's written, the inequality looks opposite to this one, but it's not, right? So just be careful you don't get thrown off by that somehow. But these would be the changes of variables, and all of the other variables would be unchanged, completely unchanged, right? These at most conditions, we're not going to deal with those yet. Okay, we're not going to deal with those quite yet. Actually, what we can say is that if x8 is less than or equal to 5, then y8 would be less than or equal to 3, right? If I subtract 2 from x8, the biggest that x8 could be is 5. So that means the biggest that y8 could be would be 3. So the y sub 3 will now be bounded between 0 and 3. All of the other variables will have the same conditions. y7 will be less than or equal to 2, and y6 will be less than or equal to 2. So this is how it's going to end up looking. But let's get the new equation plugged in, right? So I'm going to go back to the original equation here. I'm going to change all of the x's to y's, right? So the x1 becomes y1, the x2 becomes y2, the x3 becomes y3 plus 3, and all the way to the end. x8 is just y8 plus 2. And this is all still equal to 12. Okay, and so now you can cancel 5 from both sides of the equation, and what we get is y1 plus y2 plus y3 plus up to y8 is adding up only to 7. Now, this is the same thing as if you had just mentally taken 3 out of the x3 and 2 out of the x8 to begin with. You would have knocked this 12 down to a 7. In doing that, if you're gonna knock this 3 down to a 0 and knock this 2 down to a 0, don't forget to knock this number 2. That's a common mistake. People will shift this down but forget to change the 5. See, I've changed the 5 to a 3 right here. That's important. I actually prefer this also in terms of showing work, because you're not just kind of mentally, I don't like stuff where I see people just doing that and there's nothing written. I'm like, what was that? I don't get it. So it's better to kind of do it a little bit more carefully. Okay, so guys, we have a new problem now. We have a new rephrased problem in terms of the y's, and the conditions are a little easier. Every one of my variables is at least 0. We have 3 conditions that are giving us upper constraints on y8, y7, and y6. How are we going to handle that?
Subtracting by violations.
The violations, exactly. We're going to take the total. By the way, the total number of ways of solving this equation now, if we did not take into account any of these constraints, would be the 7 stars from the right-hand side, plus the 7 bars that goes with the 8 unknowns, and we would be choosing either the stars or the bars. So this would be 14, choose 7, and now what we're going to do is subtract the violations. So let me maybe do that over here. And just slow me down, guys. If you're out there in Zoom and you have a question, you're certainly welcome to just stop me, okay? We've got, I think, 4 people in Zoom and 5 people here in the room, so it's a pretty good turnout. But I am totally open to questions as we go along. So we will subtract violations. So we subtract, how many kinds of violations do I have? Looks like 3, right? There's 3 of them. There's the Y8, Y7, and Y6 that have constraints. So maybe what I'll do is make sets for those. So I'll make a set, 3 sets to represent the 3 possible violations. So a set, by the way, guys, a set is a set. So I don't want to see people writing things like C equals number of solutions of blah, 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 because that actually doesn't make any sense. This is actually a set of objects and the number of solutions would be a number. So try to be a little bit careful with this. Don't be too sloppy. I am a little more lenient on an exam than I am on homework as far as writing it out professionally but still, we should do our best to, if we're going to use sets, let's make sure they look like sets. So this would be the set A, solutions with, and we're talking about violations, let's say X6 being at least 3. Okay, sorry, Y6, that's Y6. Well, it's the same as X6. At least 3. And then set B would be the set of solutions with Y7 being at least 3. And then set C would be solutions with Y8 being at least 4, I believe. Okay. And so the number of violations is just literally the size of this union. It's just the size of this union here, which I can now work out using inclusion-exclusion. So you notice that this is actually an inclusion-exclusion problem. Size of A, size of B, size of C, and then minus the 2-way intersections. A intersect B, A intersect C, and B intersect C, and then finally plus the 3-way intersection here. Make sure you don't miss any terms on this, okay, that there's several different 2-way intersections. It gets harder if there's more sets. This one's not too bad, but it's still good to be a little bit careful with that. Let's write down these numbers in order. So the size of A, so solutions with Y6 being at least 3. So at this point, I mean, you think, well, am I going to change variables again for this? I think I'll skip it this time because all we're doing now is taking 3 stars away from the 7 that was here. So instead of 7 stars, we'll now have 4 stars. So that's going to be 4 plus 7, choose 7. I'll just write it like that for now. So where is this coming from? I'm taking the 7 stars and reducing them down to only 4 stars. I still have 7 bars, so you're going to see the 7 a lot here on the top and on the bottom. Size of B is actually exactly the same thing. And for the size of C, it's slightly different. We have to take away 4 of the 7 stars. That leaves me only 3 stars. So 3 plus 7, choose 7. Okay. And then I have to start subtracting the 2-way intersections. A intersected with B, that would be solutions that have at least 3 sesame bagels and at least 3 raisin bagels. So out of the 7 stars, I'm going to take away 6 of them right away, leaving me with only 1 star left. That's 1 star with 7 bars still, right? I am going to run out of room here. It's okay, I can get rid of this now. Then we look at the A intersected with C. So A intersected with C, oh gosh, we want at least 3 sesame bagels and at least 4 plain bagels, but you're only taking a total of 7 bagels, so there's really only one way to do that. You could write a 1 for that if you wanted. I'm just gonna write it as 7 choose 7 in that manner. But that would be the expression we would have. And then finally, well, B intersects C would be the same. So 0 plus 7 choose 7. And then finally, we have to add back in the 3-way intersection, which as you can imagine is impossible. Because I can't take 10 bagels if I'm only trying to get 7 more bagels now. So I'll just say plus 0 and impossible to take 10 bagels here. So this is a perfect example of what I was talking about earlier. You got a lot of terms here. You wouldn't need to like write down an explanation of all of them. You could maybe explain this first one and just say only 4 stars left after removing 3 sesame bagels. So you could give me a quick note of that form and then I'll understand, okay, they understand what they're doing here. And the rest of, and then for the rest of this, I would probably just say something like similar. And I wouldn't write it down every single time. Okay, so my final answer. Sometimes there's a lot of terms here and people will ask me, is it okay if I don't rewrite it all out again? Because obviously the final answer is 14 choose 7, which is the total, minus the violations. I would be okay with that if you just wanted to like sort of ditto this and put it into here. But I think it's nice to actually write it down, just so you can kind of get the look of it. So I'm gonna go ahead and do that here. You certainly won't simplify this because you aren't gonna be using a calculator. But I'm just copying down the terms that we have. And that would be like a nice looking answer that, at least without a calculator, is about as good as you could hope to do. Okay. Questions on this from either in person or in Zoom? Okay, yeah, so I think that's a pretty good first example to do. That definitely makes sense. In the other review session, the one that I sent you the video for, there is the very first problem on this session is another really good one to go over. I spent almost an hour on it. I couldn't believe it when I rewatched my video from a year ago. It's problem 1 and it has 5 parts. You're taking 3,000 textbooks and putting them into 3 warehouses, right? And there's all sorts of parts like, well, what if the books are all identical? Now, if that was the case, then it would sort of be like a stars and bars problem again. You would, just be taking 3,000 stars and you would use 2 bars to separate the warehouses, right? But then I have a part B where I say the books are all distinguishable. So that would be as if like every single one of these bagel types, like every single salty bagel could be told apart from every other salty bagel. At that point, you would have to know how many of them you had, right? There would have to be some kind of a given information about that. Otherwise, you wouldn't know how to handle it. But anyway, if the books were all distinguishable, then each book is going to choose a warehouse. So 3 choices for the first book, 3 choices for the second book, 3 choices for the third book. See, when I start talking about first book, second book, third book, I'm putting them in order. I'm distinguishing them. I'm saying they're not identical to each other. Whereas over here, when I'm just saying I want 12 bagels, I'm not saying which one you're pulling off the shelf first, second, and third. So I don't talk about it in those terms when it's a stars and bars problem. Yeah. Okay, anyway, I would recommend if you didn't get a chance to watch that review, the video of the other session, that first problem is the very first one I did in that session. I would definitely recommend doing that. Okay, that's all for this problem. I think that's pretty good on number 9. So let's pick a different one. Check that one off of my little to-do list here. Let me come back over to the first board. Move you guys over here. Hopefully you're not gonna get dizzy. And what do I want to go to next? Let's do, actually, let's do number 10 next. Let's just do the last one on the sheet. So number 10. And this one, I think there's one on, at least on one of the sample tests that's almost the same as this. It's very similar. So this one asks us to evaluate an expression. So I'm jumping all over the place with the material. We're gonna do a summation as k goes from 0 to n minus 1 of -1 to the k power times n choose k plus 1. Okay, so let's think about what this maybe has anything to do with. It's not a combinations permutations thing, but you do see these coefficients in here that we play with a lot. Does it ring any bells of any topics? Kind of like the binomial theorem. So of course, we're gonna wanna know that for the test. Let's see, the binomial theorem tells us that x plus y to the n, this is the binomial theorem, tells us that this is also a summation when k goes from 0 to n of n choose k times x to the n minus k times y to the k. All right, so this does kind of look like that to me as well. If you didn't think of this immediately, another thing you could do is you could try to just plug in some values for n to get the hang of it. And sometimes that buys your brain a little time to kind of catch up with the problem and think about it. So like if you plugged in, I don't know, n equals 1 as an example, then what is this going to be? Well, you're summing k from 0 up to n minus 1, which in this example would be just literally k equals 0. And when k is 0 and n is 1, you just get 1 choose 1. And so the answer, and then there's a minus 1 to the 0. Is that right?
Mhm.
Do I have this the way I want it? Yeah. So this is minus 1 to this, so this would just be 1. Which actually, yeah, is an example. And then you could say, well, what if n was 2? If n was 2, then I actually have 2 terms to add up here. The k equals 0 term would be, 2 choose 1, and then the k equals 1 term would actually have a minus on it, 2 choose 2. This is 2 minus 1, which is 1. And you could try one more just to really make sure you understand how the formula is working. When you plug in n equals 3, you actually have, n equals 3, you have 3 values of k, 0, 1, and 2. First, you would have a 3 choose 1. Then you would subtract on the next term, be 3 choose 2, because I'm just incrementing the k value, right? And then the third one would be 3 choose 3. So this would be 3 minus 3 plus 1, and so this would be 1. And you get the idea after a while that maybe the answer is just equal to 1. Like always equal to 1, no matter what n is. But we would need to, of course, prove it. If you just wrote this down, if this was like a 10-point problem, I might give you a couple of points. It wouldn't be real substantial, but in the case you have no idea what to do, and if you've already given it as much time as you feel you can give it, then you might just write something like this down. At least I know that you can evaluate the terms and you have some idea at least what the expression is about. But really, I agree with Lindsay, the binomial theorem is what comes to my mind when I see this formula. I've got a summation involving binomial coefficients. So can I erase the example calculations? What would you like me to do with that binomial theorem?
How do you value what x is and what y is?
Okay, think about what what we could work out for x and what we could work out for y for a value. Does anybody have an idea?
Y equals -1.
Yeah, I like y equal to -1 because I see -1 to the k in the expression. So if I plug in y equals -1, that's going to be helpful. What about the x variable? Maybe 1, right? Because there is no n minus k power over here. So I might just think it's equal to 1. So what I would do is, as soon as I figured that much of it out, I would just plug that in over here without even, don't try to force it into your problem yet. Just plug it in here and see what you get. 1 added to -1 is literally 0, right? On the one side. And then on the other side, I'm going to have summation. K goes from 0 to n of n choose k times -1 to the k. So it's going to look something like that. Now, there's a couple of things about this that don't look so good. One of them is that the limit of the sum that we are given stops at n-1. This one seems to be stopping at n. And then the other problem is that this has n choose k in it, but so according to this, it should be n choose k plus 1. So there's a little bit of a discrepancy there. It's not exactly lining up the way our formula is showing for us. So we have to think a little bit how we could make this work. Does anybody have any thought about that?
We extract the nth term.
Okay, so just to get the nth term to not show up in my summation, I could evaluate the nth term directly and see. So in other words, I think what Marcus is saying is, let's just go ahead and sum all of the previous terms. Right, and then the nth term, what is the nth term anyway? When k equals n, you get n choose n, which is 1 times -1 to the n. It would actually look like that. So that at least gets the limits of the summation working for me, but I still have the wrong binomial coefficient here for what I want. You'll notice that the terms here, they all have n choose something that's at least 1. But here, I obviously do have a term where I'm going to choose 0. So any thoughts about that part? So the k equals 0 term is also kind of bad. In the same way that we extracted the last term because we didn't really have the last term, the first term is also kind of not fitting the mold of what these terms look like because we don't have n choose 0 over here, whereas we do in this expression. So can I suggest that we kind of piggyback off of Marcus's idea of extracting a term, except I actually want to do it not with the last term, but with the first one. Okay, not that, I mean, you wouldn't know that until you played around with it a little bit, so it's easy for me to stand up here and just kind of go straight to the answer, but what was suggested already was a good suggestion, but let's just try to see what happens if we actually take out the k equals 0 term. In that case, we would have n choose 0, which is 1, times -1 to the 0, which is 1. So that first term would be a 1. And then we would be summing from k equals 1 to n of n choose k times -1 to the k. So now I have extracted the first term rather than the last term. Now you might wonder, well, why not extract them both? Why not extract the first term and what we had before, which was the last term being extracted? Well, the issue here is that this bottom number is wrong. It's supposed to be k plus 1 rather than k. And now you can see that my summation is also off. We're supposed to be summing from 1 to n here, but then in the question we were asked, we're supposed to be summing from 0 to n minus 1. Is there a way to get these summations to line up better? In other words, could I don't know if you've ever seen this, but could I do like a shift to the index? Right? So like if k is equal to going from 1 to n, could I rewrite that as k going from 0 to n minus 1 by just shifting the k that I see in the problem here? So this is n choose, let's see. So originally when k was 1, now we want to get a 1 on the bottom when k is 0. So you see that that requires me to just do that. I just have to replace the k with a k plus 1. And I have to do that here as well to make it match. So I think that should be pretty good. And now the power of -1 is wrong. So there's always something that's not quite right. But actually, so on the left I have a 0, here I have a 1. Could I just move, if I just subtract that, if I take 0 minus 1 and I just put it as a -1 on the left side, can I basically just pull out a minus sign? Let's try it. Let's just rewrite this thing. So I'm keeping the summation exactly the same, but I'm moving the 1 to the left as a -1. And then what I'm gonna do is cancel a negative from both sides. And that's gonna turn this into a 1. And it's gonna change this power. Basically, it's gonna change it, it's gonna switch the parity of it. And if we want, technically it should be -1 to the k plus 2, but that's the same as -1 to the k. And there you go, guys. That is our formula that we were supposed to come up with there. Kind of interesting. So yeah, it's, you would get partial credit just for writing this down, right? You would get partial credit just for writing this down. Every little thing you do is showing me progress towards understanding how to do this problem. So if you write down the binomial theorem, you'll get points for that. If you write down what you're plugging in, you'll get points for that. If you get here and you're stuck and you're like, I don't see how to make this look like this, you at least aren't going to get nothing out of it, right? This is really just a little trick. Actually, this shift index thing is a little bit of a trick. Keep in mind, guys, that's not the only kind of trick I've been known to do. I could tell you right now, I have not written the test yet, but all I have to do is goof around tonight in my office with this equation and say, I think I'm going to take the derivative with respect to x twice. So my first time I do that, this would be the derivative with respect to x. So I'm just playing with this for a second, just to kind of show you. I have no idea what I'm actually going to do tonight, but I could take the derivative of both sides. And I can say, I'm going to take one more derivative of both sides. So n minus 1. Now this becomes x to the, actually, why am I subtracting 1? N times, sorry, I don't know, I did not mean to put -1 there, I don't know why I did that. So the derivative of x plus y to the n would be n times x plus y to the n minus 1, that's it. So I could do that again, and so I get something like this, equals, and then over here I get whatever I get, and choose k, n minus k, n minus k minus 1, x to the n minus k minus 2 times y to the k, right? And I can say, okay, I think I'll plug in x equals 5 and y equals -2. And so I do this, 5 plus -2 would be this, and it equals to this. 5 to the n minus k minus 2 and negative 2 to the k. And then this is the only thing I show you on the paper, right? And I ask you to give me a proof of that, right? So if I said prove this equation, right? What are you gonna do? You're gonna think, okay, it looks kind of like the binomial theorem. I would start with this again, right? But this time, the key thing here is the fact that you've got these multipliers in front, right? And it looks like there's two of them that are factorialing down. That looks like two derivatives, right? And I see two numbers with two powers here. Oh, that looks like probably that's where the x and the y are gonna line up with, right? And you can start to piece that together and say, oh, I bet that's what he did. And then you can try to take this thing and manipulate it exactly as I did, okay? If I did integration, which I think was another homework problem at least, then instead of seeing these coefficients on top, you would see them like, because when you integrate x to the n, right, you get 1 over n plus 1 x to the n plus 1, right? So if you see these denominators with these factors of n in them and whatnot, that might suggest, oh, I bet he took an integral. And then you might have to think about, well, what are the limits of integration for that integral? And stuff like that. Every single one of you guys, I could recruit you guys to give me 20 different problems for my exam by just starting with this and just have a whirl at it. Do whatever you want. Plug in, use derivatives, use integrals, use shifting the index, whatever, and make your own equation, and then pass it to your friend and see if they can solve it. See if they can figure out how it works. So, or another thing you could do, if you really want to, you say, let's see if we could give a combinatorial proof of this equation now. Now, this one wouldn't make so much sense, but usually combinatorial proofs don't involve negative numbers because that doesn't line up with a real world scenario. But you could say, yeah, I guess we have, I don't know, we have n Earthlings, n Martians, and n Venusians. And we're gonna make a committee of n of them, and an Earthling has to be the president and the vice president. So here's the choices for the president. Here's my choices for the vice president, and then the rest of the committee, I basically have each person, I have these three types of people. Actually, this doesn't quite work, does it? It still has to be a 2. So it'd be something like, so for that, it would have to be 2 to the whatever, 3n minus 2. You take out the two that were already on there and then pick the rest of something like that. Anyway, you've seen stuff like that too, right? Where you have like committees and you're choosing presidents or captains or whatever, and writing down a combinatorial argument. In the first review session, I did go over a practice example of that. Would be worth watching it just to see how I wrote it up, what I actually wrote down for it. This one, as I said, this is not really set up very well for a combinatorial argument, but you could see how something like that could happen. Okay, everybody okay on that one? Great. Number 10. Let's find another good one. Well, we could go to number 2. I'll just go back to the beginning of my list here. And I'll come back over here. And let's look at number 2. Oh, we're doing great on time too, so that's good to see. So many of the topics in this class can be really tied back to functions if you really wanted to. And in fact, math is really all about functions. So it's really no surprise that we could do this. So number 2 just says, suppose you have a set X with size 4 and a set Y with size 7. And then the question has several parts again. Part A is just going to ask us, how many functions are there that go, I'll call it F, that goes from X to Y? So that would be a good way to start this off. So this is kind of the no constraints example. Anybody have any thoughts about how we might try and set this up? I like to have a picture of it actually in front of me. Like I like to actually sort of draw my X and put my my 4 elements in there. So I can just kind of have a picture to go with this problem. So that would be X with 4 dots in it. And then Y is going to be a picture with 7 dots in it. So it'd be looking kind of like that visually. And a function is going this way for right now. So the function is going from X to Y. If you were going to draw this function, what would you need to do? In terms of choices that you're making and kind of principles that are behind those choices. I'm sorry? Doesn't have to be one-to-one. Doesn't have to be one-to-one.
Every input has at most one output.
Right, so we would never have, this is a rule we cannot violate. If I have 2 arrows coming out of, I like to draw the picture with arrows. If we have 2 arrows coming out of a single point, that would not be a function. So that's not allowed. So we gotta be careful not to do that. Can we have any dots over here with no arrows? No, because the domain of the function is X. It's not a subset of X. It's the entire X. So everything on the left has to have an arrow coming out of it, but not more than 1 arrow coming out of it. Well, that means that there will be exactly 1 arrow emerging from each of those dots. No more and no less than 1, right? And so what are the choices you're gonna be making?
So each X has exactly 7 choices for each.
7 choices, right? There's that guy chooses 1, and then this guy chooses 1. You can choose the same one twice, right? And then this one could go down here, something like that. So that is absolutely good. Each of these inputs, so all 4 inputs have 7 choices for an output, and there's no constraints if in terms of repeating outputs. So all 4 inputs have 7 choices for an output. So by the multiplication principle, you can abbreviate that if you want, MP. We have, and it would be, so 7 choices, 7 choices, 7 choices, and 7 choices. That would be 7 to the 4th functions that we could make. Yeah, 7 to the 4th choices. Not 4 to the 7th, not 7 choose 4. There's lots of ways to put the 4s and 7s into numbers, but this one, it's definitely 7 to the 4th. These input values, they're all distinct. These objects on the first set are all distinct, so we're not repeating any. We could actually draw this as slots if we wanted. We could draw 4 slots. And the first slot would be wherever X1 got sent, which might be the 5th Y value. And then X2 went to the first Y value, X3 went to the first Y value, and X4 went to the 7th Y value. It's literally like making a string of length 4, where I have 7 choices, 7 choices, 7 choices, and 7 choices. You could also kind of draw it that way. Okay, let's do part B, if everybody's all right with that, which is actually now going to get to the question about one-to-one, which was asked a moment ago. Let's do a part B here, guys. How many one-to-one functions are there? This is F going from X to Y again. Okay, so we'll just add one more constraint here. Obviously, you want to make sure that the answer here is smaller than the answer here, because you're putting a constraint on it. It shouldn't be as many, right? So how is this going to change anything?
They won't have, like the second one won't have 7 choices anymore. It'll have 6 choices.
Right.
And then 5 choices.
And then 5 and then 4, right? So each additional input is restricted from using an output that was already chosen. So what we could do is we could just say that for the solution, we have 7 choices for f of x1. Then 6 choices for f of x2. Then 5 choices for f of x3. And then 4 choices for f of x4. Exactly. So there's a sort of a factorial-like expression that we're getting here, which is by the multiplication principle, we have, and this is actually p of, there's notation with this p of 7 comma 4. Right, which is just this is just that falling factorial thing where you start at the top and you go down this many steps, right? So 7 times 6 times 5 times 4 ways, or I'll just say one-to-one functions. Yeah. So I believe that's 840, but I don't even care about that, and I would not want to just see 840 as an answer. Okay, be real careful, especially if you're, so I will have scratch paper for you to use. But a couple things about scratch paper. I've become not a fan of scratch paper from in my exams because people will write on the scratch paper and then forget to tell me to look at it. I'm not just going to go looking at the scratch paper randomly. So if you're going to use scratch paper, make sure that you reference to the scratch paper, see scratch paper for details or something. Because yeah, if you over on the scratch paper worked this out and then back on the main test you wrote 840, I would be like, huh, where did they get that from, right? So I would want to see it written down. So just be careful. I don't mind the scratch paper. I understand sometimes it's necessary to have enough space, but it can get people into trouble sometimes. Okay, so far so good. Okay, let's do another part. I have one more part here, I think. What I'm actually gonna, I think, skip part C and just go straight to part D of this sheet because we're gonna have to do part C while we're doing part D anyway. So let me bring my Zoom people over this way so they can also see this. So I'm gonna skip part C because it will be embedded into part D anyway. And part D says how many. Oh, by the way, if I asked you how many functions from x to y are onto, what would the answer be? 0, because?
They need to have, each output needs to have one input.
Yeah, every output would have to have at least 1 arrow coming into it, which would mean you'd need 7 arrows, but you don't have 7 arrows, you only have 4 arrows. So it would be impossible. But I can ask you how many onto functions, I'll call this one G, from y to x are there? So that we could ask. So now we're gonna go the other way around. Maybe I'll redraw my picture here. My 7 dots are now going to be on the left side. So that's y, and I'm going over to the right side where I put x with the 4 dots. And now we're gonna call this G this time. So how many onto functions do we have? So again, onto just means that everything in the codomain, which is the output side, is going to receive at least 1 arrow coming into it. Yeah. Any thoughts about how we would approach that?
They're like stars and bars. With each being at least one.
So with each of these being at least 1, so you could sort of say that if I think of those as being, I'm sorry, those are x values. If I think of those as being the 4 x values, could we use stars and bars? And the idea being that there's a total of 7 arrows coming in. right? No, it's just good to think about this, like, you know, because that is something we've learned about, maybe this is stars and bars. So we'd have like, all of these would have to add up to 7, and then each of these would have to be at least 1. Right, meaning that, so what you would be doing is basically, the numbers here are just how many arrows are coming into them. So if I did, 4 plus 1 plus 1 plus 1, that would mean I had 4 arrows coming in there, 1 arrow there, 1 arrow there, and 1 arrow there. And we could count that with stars and bars. It would be, what would it be, 10 choose 3? 3 bars and 7 stars, there'd be 10 choose 3. But is that actually counting all of the functions that are onto? That would be telling me how many arrows are coming into each dot, but they wouldn't be saying from where. Right, I don't know if this arrow was coming from Y1 or Y2 or Y3, I don't know, and if I switch which arrows are going to which places, that's a different function, and it should be counted as being a different function. So one of the problems with the stars and the bars is, of course, it doesn't keep track of the order. So I don't know which of these, if I knew which arrow came from Y1, Y2, Y3, Y4, and so on, and we had them labeled as such, maybe with different colors or something, then we would get the right count. But the stars and bars is blind to that. The stars and bars does not know where these arrows came from. It would just be telling us how many arrows we had coming into those dots. So I would maybe vote against stars and bars for this one.
That's because the stars are kind of like identical inputs, right?
Yeah, if all of these were somehow identical,
Yeah.
and we weren't distinguishing these inputs, then you're absolutely right. We could think of it as, there'd be less functions that you could make. But at that point, I don't even know if it would make sense. Because with your function, you have an input set that consists of a bunch of distinct inputs. Did you have an idea?
I was thinking if it can use violation against that.
Can we answer this problem by doing violations, maybe counting how many functions are not onto and subtract from the total? I always have to make sure that if I'm gonna do violations, I always wanna make sure that that problem is gonna be easier to solve than just the original one. Okay, so just keep that in mind. We don't wanna do a violations approach just for the sake of doing violations, right? So the question is, would that be easier? Would we say if a function fails to be onto, then that means there's a dot over here, at least one dot over here that is not receiving an arrow at all. And could we count functions that are not getting arrows to all of these dots easier than the original problem? Actually, if that was the case, then we're gonna subtract from the total, right? By the way, what would the total be here?
4, 7,
So first dot has 4 choices, second dot has 4 choices, third dot has 4 choices. So this would be the total without constraints. And then what we would do is we would subtract the violations. Right, so a violation is a function that's not onto. Can we present that in a way that makes it sort of easy to work with and count?
Can you create a set then use it as an inclusion and exclusion where you can let set A be where x1, there's no arrows on the x1, x2, and x3.
Okay, we could say, well, what are all the functions that never hit x1? If they don't hit x1, then that means there's going to be 3 to the 7th of those. Because every arrow is going to have 3 choices instead of 4 choices, but we already kind of know how to do that kind of a number, right? So what we could do is, for the violations, we could make 4 types of violations, right? I could say, well, A1 is the set of functions with x1 not in, I'm gonna use some function notation here, guys. x1 not in the range of f. Okay, so RNG is the range of the function, so let's assume that x1 is not in the range of the function. And then the second one would be functions with x2 not in the range. And then A3, a set of functions. You can use these ditto marks, guys, if you want to save some writing. I don't mind that at all. And finally, A4 would be the set of functions with x4 not in the range of f. Right, so we could do that, and then our violations would be the union of all of those, right? Which I'm gonna need a little bit of room, I think. Okay, so I kind of like this idea. So we have those sets, and so the size of the union would equal, instead of writing out all the terms of this, let's just think about it in terms of how many sets we're working with at one time. There's 4 singleton sets, right? 4 singleton sets. So I'm gonna start with 4 times, what's the size of A1? So A1 is functions where x1 does not have an arrow coming into it at all, which means how many functions will I have where, and I don't know about the x2, x3, and x4. They could be anything. So you could have other points here that are not being a part of the range. But the only thing we know is there's nothing coming into x1. And I'm making a function that has nothing going into x1. How many of those, how many ways would there be to make a function that specifically avoids x1? 3 to the 7th, exactly. Great, so that's by the kind of the same reasoning. And we have 4 of those kinds of sets, okay? Then we have to subtract the intersections. Now, how many different intersecting pairs can we make here? 4 choose 2. So that would be, A1 and A2, A1 and A3, A1 and A4, A2 and A3, A2 and A4, or A3 and A4. You can write that all out if you want to, but you keep in mind, I told you earlier, my exams are not known for being super short. You start writing out too many things like that, you're gonna be feeling like a lot of time is going by. So I think it's just easier to say, wait a minute, there's gonna be 6, which is 4 choose 2. I should write that as 4 choose 2. There's going to be 4 choose 2 terms where now, let's just look at the first one. If I avoid x1 and x2, how many functions can I make? 2 to the 7, exactly. 2 to the 7, great, So you'd have that. And then we go back to plus again, the 3-way intersections. All right, how many different 3-way intersections are there? 4 choose 3, which is 4, right? So there will be 4 of these. This is going to be 4 choose 3. I'm using the fact that there's symmetry here, right? The size of any 2 of these being intersected is always 2 to the 7th. It doesn't matter which one it is. So I'm taking advantage of that. And then this will be times 1 to the 7th. You are forced to send that all 7 arrows to the same point. And then finally, the 4-way intersection, there's only 1 of those. And well, now you're saying how many functions don't hit any, how many functions have nothing in the range? Well, that's impossible, right? Because you've got to send the arrows somewhere. You could think of it as 0 to the 7th if you wanted, but it's basically just 0 at the end. So this, whatever this number is, would be your violations. And so your answer would be the total, which we said was 4 to the 7th. And then we would subtract these violations. 4 times 3 to the 7th minus 6 times 2 to the 7th plus 4 times 1 to the 7th minus 0. And that could be a good answer. Right. That look okay to everybody? Okay, so that's actually inclusion, exclusion, but this time not with a stars and bars thing where you have a bunch of combinatorial binomial coefficients being added and subtracted. This time you have powers of integers being added and subtracted. Because in this case, the order does matter, right? The order matters here, whereas in the poppy seed and bagel, the different types of bagels problem, the order that you picked up those bagels didn't matter, even though you still had a stars and bars phenomenon going on there. Yeah, so, okay, so it's kind of a nice example about counting functions that have certain properties. Question?
You said we were gonna answer part C and part D. Would you mind highlighting where that?
How many part C just says how many functions are there from Y to X, and that would just be this number. So this is actually part C, thank you, yeah. Yeah, good point, good point. Okay, let's go to number 5B. And so I'm checking off my sheet here. 5B, and I'll put it over here. And I'll have to explain, I did 5A in the first review. So if you're interested in that, you can watch that one later. But here is what 5B is about. Well, actually, so first of all, part A is a formula for the number of derangements, which is n minus 1 times the quantity of dn minus 1 plus dn minus 2. So part A of this problem was to prove this formula. And I will tell you that basically what it is you're just using the derangements formula. So you need to remember the formula for d sub n. Does anybody have this memorized yet?
So one,
You want to factor it out?
No,
Just,
that's fine.
huh?
No, we can go that multiplied.
Okay,
Yeah,
fine. 1,
minus 1/1 factorial.
Uh-huh.
Plus 1/2 factorial.
nice,
And then
and dot, dot, dot. And what's the last term?
-1. And then
Awesome. Everybody has that down? Yeah, that's the derangements formula. So if you plug in the n minus 1 version of that right here, and the n minus 2 version of that right here, so you just put them side by side, add them together, and then put this n minus 1 in front. If you work it all out, it's kind of a mess, but it's just algebra. I have it all typed out here, the solution, and I went through it in the other video, so you can watch it if you're interested in seeing the details of that. But what I want to do with you guys now is focus on part B, since part A, as I said, is already kind of taken care of. I'm going to erase this formula. This is a good one to know for sure for the test, but I'll erase it for now. And what I'm going to ask you in part B is to show, so this is going to be a proof, show that dn is even if and only if n is odd. So for the odd numbers, there's an even number of derangements. For the even numbers, there's an odd number of derangements. So I don't know if you remember this, but if there's only one thing that you're deranging, then it's impossible to derange anything. So 0. If you had 2 objects, there's only one way to derange them. If there were 3 objects, you would have 2 ways to derange them. We wrote all these out in class. And then when there's 4 objects, we got as many as 9 ways to derange 4 objects. So what you're noticing is that it's flip-flopping between even to odd to even to odd, back and forth, but the subscripts are the opposite parity to the number. And this is actually asking us to prove that that's not just a coincidence, but it actually is always going to happen like this. So the subscript being odd means you get an even number of derangements and vice versa. Yeah, so because this is a if and only if statement, we actually have to prove it in both directions. So we have to prove if this is true, then this is true, and if this is true, then this is true. To kind of go both ways. Is either of those ways look maybe easier than the other one? so, sorry, is left or right? Going left to right, or is going right to left? Which one of those is easier, do you think?
Right to that?
This way? Let's see if that's the case. So if I go right to left, let's assume, actually, I agree with you.
Okay.
I like to just not give it away immediately. But I actually like that. Assume that n is odd. If n was odd, can you explain why the dn would have to be even? Yes, Marcus.
By that formula that we have. And minus
Formula
one,
here, okay?
If it's odd, I guess you could do like a 2K if you want, but
That's
it
okay.
becomes even if you subtract one.
Okay, so n minus one is even, right?
Addition parity theorem.
Perfect, so this is whatever theorem that is, I've never heard of it. N minus one is even, and so you have an even number times something stays even, right? That's just kind of given. By the way, I'm teaching number theory next semester. So if you have questions about even and odd, you should definitely take that class, but it will be much more than that, trust me. Anyway, yeah, so in this case, so thus, n minus one, if you take an even number times anything, times any integer, that is even, and so d sub n is even. Okay, so I agree with you guys that that is the easier direction. So you would start off by writing that down. Okay, so we have that. Now, in going backwards, I think it's a little hard to sort of say, well, let's assume that dn is even. In other words, let's assume this entire thing is even, and then try to figure out something about n itself, which is just sitting inside of the expression. I would tend to want to do this direction by contrapositive format of this statement. In other words, the negation of this one implying the negation of this one. So what that would start off with is assume, you could even call it, if you want, you can just call it by way of contradiction. To kind of go backwards. Let's assume that n is even. So assume that n is even, and now we need to show that dn is odd. Right, so now we're kind of switching the even and the odd around a little bit. So if n is even, we want to show that dn is an odd number. Now, we are still going to be using this formula that we came up with before. Now, if n is even, then by the addition parity principle, is that what it's called?
Maybe it's subtraction for this,
Somebody-
whatever.
I don't even know what it is, but anyway, I've never heard it. Apparently I missed that day in school. So if n is even, then n minus one is odd. Okay, great. So this guy is odd. But I want the whole thing to be odd. That's what I'm trying to prove, is that the whole thing is odd. I've got this part being odd, but in order to conclude that the whole thing is odd, I would need this one to be odd as well. So I'm gonna put a question mark next to that because I don't quite know for sure that that's the case yet. Now, what I can do is I can remember what I just proved. I proved that if something is odd, then the d of that is even. So I do now have n minus one being odd, which means I do know that dn minus one is even by the part that we already proved. Now, this would rely on you having done this part first. If you haven't proved that first, then you wouldn't be able to use that yet. But anyway, so this one is even. And my goal, of course, is I want the whole thing to be odd. Right? This one being even, so that actually means if this is even, then this one had better be odd. Right? I'm just looking at this part. I need this to be odd so that this whole thing will be odd. And I get an odd result for the formula. So now what I really need is this d sub n minus 2 is odd. That is what I need a reason for. Now n minus 2, oh, let's see, that's back to being even again. And we don't know, that's would be begging the question, if the subscript is even, we're trying to prove that D of that subscript is odd. So I have to be careful that I'm not using what I'm trying to prove, right? Because the n minus two is still even. So what would be like, without like accidentally getting into trouble here, what would be a proof strategy? And I know I haven't used it much in this class, but we are gonna be using it like crazy, starting in chapter 7. Like, is there a proof technique for this? You're trying to prove something about n, but see, you already are basing that off of, say, some earlier value of n. Induction, yeah, induction. Have you guys seen that, right? In like your proof class, right? This is a smaller value of n, and we could assume by induction that we've already proven that for smaller even values of n, that d sub that value is odd. So I'm just going to say by induction on n. So now, normally when you do this, you should set up your induction with a base case. Like, you know how it works, right? You have a base case for your induction and then you kind of prove from there. So of course, we have all the base cases in the world that we could ever need right here. So we can certainly check that, if we're trying to prove that D sub 4 is odd, we of course are allowed to use that D sub 2 is odd. It's like the previous case, that's like your base case from there. And then you just assume how the way induction works is you assume that your statement is already true for earlier or smaller values of n. And so in that case, a smaller value would be n minus 2. But you do have to have a base case. Because like if you were trying to do this for n equals 2, then you would be basing it off of n equals 0. Which I guess we don't have. I guess you could define D. Do we have a value for D sub 0? I think I called it 1 as just a formality, so to speak. But anyway, there's always got to be a first value that has to be sort of explained on its own footing before you can use this what's called induction step. Right? So without going into a whole big lecture about induction, basically, this is the way you would need to do this. You would do induction on n, assuming that it was already true that d sub n minus 2 was odd, and now you're proving that d sub n is odd. Okay, so this means that d sub n minus 1 plus d sub n minus 2 is odd. Because you're adding an odd number to an even number, which gives you an odd number. Notice I'm not bothering with, oh, here's an even number and then here's an odd number. I mean, you could put all that into the proof if you wanted, but it just adds notation that you don't really need. You can just refer here to even numbers and odd numbers, and you get an odd number here. And so thus, by part A, the formula in part A, D sub n is also odd. So that has just a little wrinkle in it with the induction at the end. I'm not probably a huge fan of that question, just because how many times have you guys done induction this semester? Probably not at all. Now, on the next exam, it'll be a different story because we're going to use induction a lot. I don't like writing questions where sort of out of the blue, something we never really used is going to come up. If I do allow people to take a part or two home, I feel a little less guilty about it potentially, but I still don't like it. I don't like putting questions on that we really haven't seen, even if it technically is something everybody's supposed to know coming into the class. But this is just a review session, so I can do whatever I want in the review and not feel too bad about it. And I think that was maybe a reasonable question to look at. Okay, I'll cross that one off, and I've only got 2 more on the sheet here. Are there any questions on that though, by the way? Okay, let's do number 4 next. So this one has a little bit of words to spell it out. So prove And there will be proofs for sure on this exam. There's plenty of computational stuff, but you should expect proofs anytime you're in a sort of a pure based 400 level math class. Out of a set of 217 integers, okay, we can always choose a subset of 13 of them. Out of these 217 integers, we can always choose a subset of 13 of them so that the difference of any two chosen numbers is a multiple of 18. Okay. So it's a proof, although it's not terribly abstract because we have specific numbers here that we're playing with, but does anyone have just off the top of your head, the idea, like what does this have anything to do with? Pigeonhole principle? Yeah, I think so. Partially because I think I gave an example very similar to this already. And yeah, we haven't really reviewed this a lot lately. By the way, so you should definitely go back to the pigeonhole principle again. If it's been a while, remember the fortune cookies example? Of course, there's the birthday problem. How many people do you have to have so that, 75 people all have the same birthday, stuff like that. And I like to model those out of worst case scenarios, right? You get as unlucky as possible for as long as possible, then like how long is it gonna drag out? Those kinds of things. There's also the clever application of the pigeonhole principle, which I would never ask you to do, except that I've shown you several examples of it. The one about the child watching television for a certain number of days and a certain number of hours, at least 1 hour per day. And then after 2 weeks, they had watched, I don't know, 70 hours of TV, whatever it was. And you had to prove that in a certain interval of time, the child had watched a certain amount of TV. So, something like that, where there was an example, I did it in the videos, and then you saw in the homework an example of it. Something that comes up more than once like that is something that you should be able to do, even though, yeah, if you'd never seen it before, you probably have, I didn't know how to do it, actually, before I, kind of got the hang of how those problems work. So it's something you should be ready for. So yeah, don't forget to go back and review the pigeonhole principle. I'm just mentioning that because one of the other class that I teach is 250B, where everything builds on itself constantly, and the students can't forget everything because they have to keep using it constantly. This class is a little different. We sort of go in different directions, and if you aren't careful, and something could kind of slip through the cracks after a few weeks. So definitely worth going back. So if you're thinking pigeonhole principle, first thing I would do before I did anything else on my exam is I would write that down. Because I can give you credit for pulling the right tool out of the toolbox, right? So the fact that you know that this is going to use the pigeonhole principle, if this was a 10-point problem, I would give you probably a point or two just for writing this down, okay? The next thing you want to do with this kind of a problem is think about the pigeons and the boxes, and how you would be setting that up. So this problem is not really a word problem about anything other than math. So what we have to do is think about how we would set up boxes for this. These kind of look like my objects, right? These integers are going to go into boxes. So how would we set up boxes for this? Go ahead, Kevin.
Since the problem is asking about the multiple of 18, the first thing I'll think of is the mod 18.
Yeah, we're trying to get two numbers to be multiples of 18 together, any two chosen the two chosen numbers have to be multiples of 18 in the terms of their difference. When you're talking about multiples of n and you're looking at differences, that really does suggest basically boxes for the remainders, mod 18, right? So we would maybe try that. So let's do that. We set up boxes to represent congruence classes. If you don't use this fancy language, it's okay. Congruence classes, mod 18. If you didn't like that phraseology of it, if somehow you didn't take Math 302 or something like that so far, you could also just say remainders in in dividing by 18. So you could give it in simple language if you wanted to, but and then it doesn't hurt to draw a little picture, although technically this really shouldn't be in the middle of your proof the way I'm doing it right now. It's kind of getting in the way. Maybe off on the side, you have your possible remainders in mod 18, okay? Now it says choose that we can always, show that we can always choose a subset of 13 of these numbers such that any two numbers from those 13, the difference is a multiple of 18. So if I had 13 numbers that were in the same box, then all 13 of those numbers would have differences. If I subtracted them against each other, those differences would be a multiple of 18. So I'm trying to prove that there are 13 pigeons in one box right here. I have this many integers to play with. So how would I argue that, do you suppose? Oh, before we do that, I have to explain how am I putting the objects into the boxes. So you not only have these, the boxes, we should also say the 217 integers are the objects. And then we have to explain, so try to check yourself on this if you're doing one of these. Did I explain what my boxes are? Did I explain what my objects are? And then did I explain how I'm going to put those objects into the boxes? So in this case, we could add a sentence to just say, we place each integer into the box. And then you have to explain how you do it. According to its congruence class. And that would of course be mod 18. So in mod 18, we would figure out, well, what is the congruence class for each integer? And that's how the integer goes into the box. Okay, so it's a good thing to check off. Did you explain what your boxes are? Did you explain what your objects are? And did you explain how you're putting the objects into the boxes? Now, let me get back to my question. I would like to show that 13 things have ended up in the same box. So what would be a good way to argue that?
Like that worst case scenario thing, give you at most 12, you get to 16.
Okay, if we kind of go, I almost like to think of it as, it's really like by way of contradiction. Suppose that you do not have any subset of 13 integers where the differences of any two are a multiple of 18. So which is kind of a worst case scenario, if there is no box with 13 objects in it, then we have at most 12 objects times however many boxes we have, which is 18. So you could have 18 boxes that would each have 12 objects in them. And if you do the math on this, it comes out to 216 integers. And that's a contradiction. Yeah, so that's a contradiction in that case. Make sense? A lot of times this divisional principle is kind of like mostly just common sense. I mean, you can put it into formulas. You can say, well, if I have Q boxes and I have N objects and I want to get at least K objects in one box, then I have to sort of take Q times K minus one and add one to it. Like, I don't know if those are the letters I used, but I stated this sort of in my videos that you watch, the general pigeonhole principle, and I had all this kind of formula written down, but you don't really need it for the most part. So here I'm just using common sense and saying, well, if I don't have the plus one, then that's not enough objects, right? I have 18 boxes, but I only have K is 13, so I have only 12 objects per box. That's 216, and I would need one more than that to make sure that there's a box with 13 objects in it. I could probably make this a little bit harder. It's not really much harder, but I could make this number something that's not exactly one more than what this would dictate, but it would be the same contradiction. Like if I put 219 here, you still have the same conclusion as long as I'm above 216. Yeah. Okay, so yeah, it's not a terribly creative example. I guess I wasn't coming up with anything too creative for this, but definitely review the ones that you saw me do in those videos during the week before we actually got back in person. Just wanted to get that back in your head again. Okay, there's one more on this sheet, and then together with the video review of the other 5 problems, we will actually have covered everything. By the way, so the other 5 problems, let me just quickly, in case you have not watched that video, tell you what they're about. The first one is just counting permutations and combinations, and there's stars and bars and all that kind of stuff. So we've seen some of that. There's a problem about a coefficient of a multinomial expansion. So the multinomial theorem, again, I did that in my other review, not in this one, but it's something you definitely should look at. We proved that derangements formula that I just erased. What else? Oh, I did a combinatorial argument in that other video, so that's something for sure. I almost guarantee you're gonna have that on the test. And then there's one about, that's actually just another inclusion exclusion, similar problem to something we've done before. So it's not really that bad. So let's just do this last one. And I kind of saved it for last because it's a little bit tedious. But it's one of these problems. You'll probably, the biggest thing with this is to just recognize what it's about. So we have 5 employees. They are Jack, John, Joe, Jim, and Jerry. And they must take, I'm going to kind of paraphrase this to make it short. They must take a 1-hour shift between 8 a.m. and 1 p.m. So I believe that's that's going to be 5 hours worth of shifts, and we have 5 employees. This is supposed to be John. Jack, John, Joe, Jim, and Jerry. And so between 8 a.m. and 1 p.m., they each have to take a 1-hour shift. But then the question is, how many ways can we assign them? So how many possible assignments, given there's some constraints here. The first one is that Jack can't do 8 to 9 or 11 to 12. And John can't do 8 to 9 or 10 to 12. And Joe cannot do 11 to 12. And Jim cannot do 9 to 11. And Jerry cannot do 8 to 9 or 12 to 1. So they have these times that they're not available to do this work. So before anybody says anything, I want you to just quietly to yourself, ask yourself if you know what kind of a topic this is, like what kind of a problem it is, and then in a minute, I will see, because this is actually a big part of it is just knowing what this is about. How many of you think you have an idea what this has to do with? Kind of, okay, see lots of nodding and hands. Yes, what is it? Jean? Yes, forbidden positions, exactly. So you want to recognize that. And if you, I mean, let's just say you're like, there's 30 seconds left and then you have to turn in your test. Just write this down so that I can give you something for knowing what kind of a problem it is, like what the tool is for the problem. So yeah, it's a forbidden positions problem. And when you have a problem like this, you almost always want to draw the little checkerboard picture, right? So we have this little, it's a 5 by 5 in this case, 5 rows and 5 columns. And now there's a couple of ways to set this up. You can put the people on one axis and the hours on the other axis, but it's not, nobody's telling you which way you have to do that. Maybe I'll start off, I'll put Jack here, and then I'll put John on the second row. And then so I'll put the staff on the different rows, Joe, and then Jim, and then Jerry. And then I'll put the shifts up across the top, 8 to 9, 9 to 10, 10 to 11, 11 to 12, and then 12 to 1. Maybe draw it like that. And then we just have to cross off the times that they can't work. So Jack cannot work from 8 to 9 or from 11 to 12. Just put an X in those places. John cannot do 8 to 9 or 10 to 12. So put X's in those. And then Joe cannot work from 11 to 12. And then Jim cannot work from 9 to 11. And then Jerry cannot work from 8 to 9 or from 12 to 1. So I think I did that correctly. And again, you guys probably remember, because we just did this last week, it's a little tedious to do this process. But if you wrote down forbidden positions and you drew this grid, you have to understand you're going to get a lot of credit for at least getting it set up. And there's kind of diminishing returns with this, because what I mean by that is in terms of like your strategy for the exam, if you have a choice between having to solve a combinatorial argument and getting like a good bite into a problem like that versus like sitting around for 15 minutes doing these R values, I would probably do the combinatorial argument, right? Because this gets a little bit time consuming and tedious if you really go at it full steam. By the way, if we had switched this around and put the hours on the rows and we put the people in the columns, that would also be fine. It would essentially transpose this grid. There are some situations where that could make it easier. If you end up with rows that are empty, it's always a good thing, right? That's always easier. Now, in this case, I think if you tried to flip the rows and columns, you wouldn't gain much from it, because all of the rows and all of the columns have some X's in them. So I'm just going to leave it like it is. But just keep that in mind, that it could be possible to improve your counting. It's not really improving the strategy, it's just making it less tedious by flipping it around. Anyway, so the formula, as you probably remember for forbidden positions, is, this would also be good to write down if you were running out of time and didn't want to do the whole thing. It's n factorial minus r1 times n minus 1 factorial plus r2 times n minus 2 factorial minus da 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 da, and then finally plus -1 to the n times Rn. So again, there's more partial credit for you for doing that. The R1 is an easy one. That's just the number of X's in the whole picture. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So R1 would equal 10 for this example. By the way, N is 5. So N is 5 on this problem, and then the R1 would be 10. Now, for the R2, you want to break this down into choosing 2 of these rows at a time. I like to sort of just go in order like this, R12, R13, R14, R15, and then I'm adding all of this up, R23, R24, R25, and then R34, R35, and then R45. So I'm gonna get 10 numbers here. You don't really have to write this down on your paper. You can just start writing out the numbers. The thing I would recommend though is that you don't just write the final, again, if you do this off on scratch paper that I never see, and you just have a number here and it's wrong, I'm gonna be like, oh, they don't know how to do this, right? But if I see all 10 numbers and I see that, well, one of them is wrong, but the rest of them are all good, then I'll be like, okay, they know what they're doing. They just made a little mistake on one of them, and I can live with that, right? But you basically go in here and you look at your picture and you just say, how many ways can you choose to create a violation in both of the 2 rows you're focusing on? So for the first 2 rows, right? So remember how we did this pretty recently. I can pick this X along with either of these 2. Or I can pick this X along with either of these 2. So that would be 4. And you don't need to explain that, by the way. If you tried to explain every one of these every time, it would drive you nuts to try to explain it. Let's see, R13 looks like it's gotta be this one with this one. There's only one way to do it. R14, I believe, is 4. And R15, I believe, is 3. And then R23 is 2. And R24, I know I'm going kind of fast, but it's okay. 2, 3, 4, 5. And R25 is 1, 2, 3, 4, 5 also. And then R34 is 2. And R35 is 2. And R45 is 4. Let's see. 5 plus 7 is 12, 14, 24. 24 plus 8 is 32. Now I get to check my solution key. Ah, I got 32. So that's pretty good. Okay, so that's how R2 works. Any questions about any of those numbers? Try not to get, my big thing here, guys, is try not to get hung up on this on the test. Okay, you could lose a lot of time like getting all flustered with calculating all these numbers, and I'm like, whether you got them right or whether you got them wrong is probably the difference of a couple of points on the whole exam. It's much better to like get the rest of the exam done, right? So just don't get caught up on this, because now you got to do the R3. Would you like me to do it? I guess it's just right at 7. I'll do R3. Okay, I'll go fast. There's no more terms than there are there. 1, 2, 3. Here the key thing, guys, is don't forget to do all of them. It can start to get easy to miss one. 1, 2, 3, 1, 2, 4, 1, 2, 5, 1, 3, 4, 1, 3, 5, 1, 4, 5, 2, 3, 5, 2, 4, 5, and 3, 4, 5. Look good? Did I tell you guys at the start of the semester, sometimes I like to make mistakes on purpose just to see if anybody's paying attention. Sorry?
2, 3, 4.
Yes, I just left this one off to see if anybody was paying attention. That's what I was just talking about. Don't forget to make sure all of your terms are written down. So the R2, 3, 4 needs to be there as well. Okay, so we're gonna do this kind of fast because I want to go to dinner. So rows 1, 2, and 3. With row 3 is a nice one because I have to pick this X. And if I'm picking that X, then I'm only looking really over here, and I would have to pick this X and this. There's only one way to do it. So that's just a 1. And then 1, 2, 4. I have to pick this X. And then in the second row, I could pick this X, and in the fourth row, this X. Right? So that's one way. Or I could pick this X with this X and then either of these 2. So that's 2 more, so it's a total of 3. Okay, again, don't freak out about this, if you get like a little flustered, this is not gonna make or break your test. R1, 2, 5, so I take this one, and then this one, and then maybe this one, that's one way. Or I can take this one, and this one, that's 2. Or I pick this one with this one and this one, that's 3. Or I pick this one with either of these 2, so that's 4, 5. So I think that's 5. Yes, okay, all right, and then we have our 1, 3, 4, right? 1, 3, 4, so I have to pick this one, and I'll have to pick this one, and I pick either one of these 2, so that's 2. And then our 1, 3, 5, well, I'm gonna pick this X with this X, and then I have to pick this X, there's only one way to do that. Okay, our 1, 4, 5. So I'm taking the bottom 2 rows. So if I pick this X, then on the bottom I have to pick this X, and I have 2 choices here. So there's 2. Or I can pick this X, in which case I have 4 choices of how I mix and match the bottom 2 rows. So that's 2 plus 4 is 6. Okay. And then 2, what's the next one? 2, 3, 4. Okay, 2, 3, 4. So I'm gonna pick this one for sure. So I have to go to rows 2 and 4 and work on these X's here. So I could have 2, 3. Okay, so I think that one's 3. And then 2, 3, 5. Again, I have to pick this X. So I can pick this one with the one in the lower right corner, or I can pick this one with either of the 2 in the lower right corner. So I think that's 3 more. And then 2, 4, 5. Okay, I picked this X for sure. That means I have to pick this X here. So I have 2 choices for one of these X's. Or I pick, so that's 2 so far. Or I pick this one together with this one, together with either of these 2. That's 2 more choices for a total of 4. Or I pick this X, and then I have 4 choices of how to mix and match the bottom row there, and that should be a total of 8. Okay, and then finally I have to do 3, 4, 5. I think 3, 4, 5 is just 4, because you have to pick this X, and then you have these 2 and these 2 that you can mix and match. Okay, what does that add up to? 9, 10, 11, 12, 21, 32. Is that 36? What do I have in my notes? I have a different number in my notes.
I think you got a row 1, 2, and 4 wrong.
Yeah, this one here is not matching up with my solutions. Thank you. 1, 2, 4, I did it wrong. So if this is what I came up with, right? I would probably not even take off a point, to be honest with you. Like if you got 9 out of the 10 numbers right, I could see somebody making a mistake on this. So try not to freak out, but let's see, what did I do wrong? 1, 2, 4. So that's this row, and this row. So if I pick,
I think you didn't account for the second X on that first row.
oh, I didn't. So let's start over. So if I pick this one, then I can pick, sorry, I pick this one and that one. So that's 1. Or I pick this X with this one and either of those 2, that's 2 more, that's 3. Or I pick this X with this X and either of these, that's 4, 5. Or I pick this X, and this X, which is just number 6. Or I pick,
No,
That's it, I
that's
think.
it.
that's it. Oh, 6. Oh, that's what it's supposed to be. Oh, that's what it's supposed to be. Okay, it's supposed to be 6 and I had 3 there before. Okay, great. So just made a little typo. So that one comes out to 39, right? 39. The R4 value, do we want to do it or you had enough? You know how it works, right?
Yeah.
Okay, I won't do it. It's in my solutions. So you can read these solutions. I'll leave that to you guys along with the rest of these problems in this review session. Any other questions I could go help anybody with today? I'll tell you my plan. I'm gonna go off campus for about an hour and then I'm gonna come back. I'll be in my office all evening and I'll turn my Zoom on. If you're either here, that's great. You can ask me questions. If you go home and you want to talk to me, I should be in there pretty much up till midnight. So feel free to do that. And tomorrow I should come in around a little before 9. I do have 4 hours of Math 250B though. I have a break from 12 to 2. So if you think of anything kind of that you want to ask me about kind of last minute, 12 to 2 would be a chance to do that as well. Or you can just shoot me an email if it's 3 a.m. Is that you have a question? Shoot me an email. When I wake up, I'll answer it as soon as I can. So, but thanks for coming. I appreciate you guys in Zoom as well. Thanks for everybody coming today. I'll send this out in case you want to watch it, but I hope that it was helpful and see you guys again soon. This is fun stuff. I love it. All right. Bye for now, guys.
Thank you, Dr. Evans.
Thank you, Dr. Edit.